So let me start by saying that, a lot of people who worked on this problem for many, many years. So this is a 50-year-old problem. And a lot of advancements have been made, mostly due to the advancements in computer technology. So I have here two pictures. The first shows how in '61, the Japanese were doing vowel recognition, and you used a computer full of, a room full of computers, or whatever these things are. And this is how we do it now, like with a little laptop, and you do a voice command system through that. So there has been a lot of progress. And it's not only because of the computers. The problems that people have been tackling are getting more and more difficult. This is out of the Professor Furui's plenary talk in ICASP. It shows how, we moved from simple tasks of so small vocabulary, voice command, from the 80s, to go all the way to natural conversation transcription and two-way dialogue systems in the 2000, after 2000. So the problems are getting more and more difficult, and our results are getting better and better. This is another historical chart that people like to show to the funding agencies to show that we actually have progress. So what this shows is, again, DARPA has been funding projects in speech since the 80s, and they have regular benchmark tests and evaluations to measure the progress. And the first tasks were very easy and small vocabulary, and you see that the first time you tackle a task, the error rate is high, and then as more years we're working on it, the error rate goes down, and the goal is to bring basically. Okay. I thought this building was modern. Okay, and this intimidates me. To bring the error rate down to.
So we should be intimidated.
Okay, to 10% for all the difficult tasks. Oh, thank you.
So this is 10, okay, error rate, that's what it is.
This is the error rate, yes. So the interesting thing, when I started working, in switchboard, we were at 50, 60% error rate. And now it's actually 12 to 15. So we are close to this point that they were projecting. So what have we done? What have engineers done to actually address this very difficult problem? And even though they haven't solved it completely yet, and there are a lot of new ideas being introduced every day, there is an infrastructure that has been set from actually maybe 30 years ago that has remained pretty much stable. So what is the approach that has been taken? You treat this problem as a noisy channel problem. You have an input, that comes from the speaker's mind, and at the end, you want to predict or give a hypothesis of what is the most likely sentence that was actually produced out of all the sentences in the language. So let's look at this channel a little more detailed. So the first part of this channel is a speech producer. This is the human vocal tract, basically, which is, it consists of 4 basic cavities, like the larynx, the pharynx, the oral cavity, the nasal cavity. And, all this system is, it's basically, all of these components are contributing in producing the speech. So I have a very old clip here that shows how everything moves when speech is produced. Let's see if it plays. 1 second. So you see how everything from the back here, basically. This is a sequence of X-rays. I think this thing was from the 70s. Very, very old. I like old stuff. See, all of the stuff move from here. The tongue moves up here, the lips, everything. So the way all these things move, basically what they do is produce, speech, which propagates through the air as a waveform by changing the air pressure changes around the basis vibrating point. And as this signal goes through the air, if you talk to a microphone, these changes in air pressure convert to basically changes in electric voltage, and you can observe the signal. So by looking at the signal, you basically can never tell what was said. Nobody can. But what people have found is that if you take the spectrogram of the signal, which is basically a sequence of very short windows of frequency analysis, right? And you create this thing, then actually you can read this. There are people that get trained to read the spectrogram, and they can understand what speech it represents. So basically, yeah, it's this frequency analysis that is very important to understand what is the underlying signal. So when we extract features from the signal that we want to use to do speech recognition, that is a basic principle. You take the signal, you define a small sliding window, and then for each, you call this like basically a frame, and then for each frame, you extract a feature vector. And this feature vector contains information about the spectral content of the signal. More specifically, a very well, common example of acoustic feature vectors is what we call Mel frequency septal coefficients. Okay, I'm not going to go through all of this in detail. I just wanted to scare you by showing you how much signal processing is being done. Basically, this part here is what defines the MFCCs, what we call Mel frequency septal. There is a discrete Fourier transform. There is a discrete cosine transform, what this is here. And there are some other filters that basically, this filter here, this filter bank, kind of models the way the human auditory system works. The basic thing out of this is that what you end up is you get the speech signal, you window it, and then you slide the window over. And what you end here is with vectors, right? So what you do, you have 13, actually 12 coefficients, spectral septum coefficients. You add the energy, and then you have 13. And then you take derivatives and second derivatives, and then you have 39. So this is your observation vector, let's say, at this channel. There are other representations of acoustic features. There's the PLPs that actually are also very common. There have been neural network features, articulatory features. There has been a lot of research on how to actually find the best acoustic representation. But anyway, so this is very old, and I think it's still very widely used. Okay, so what happens to? So this is now the O. The O is the acoustic feature vectors. The last part of this channel problem is basically the decoder. So what we want is, given that we observe these acoustic observations, we want to find the sequence of words that maximize the probability of the words given the observations. So we use Bayes' rule to rewrite this. So why do we use Bayes' rule? Basically, it's very difficult to come up with a predictive model like this, right? So it's easier to break it down into different components. So if you rewrite it like this, then you can ignore the denominator because it's common among among all the hypotheses, right? It's a given signal. So all you end up is with a numerator, which has two components. Here it is again. The first component is actually called the language model, and it's the model that models the source, which is the sequence of words that were thought or were formed at the speaker's brain. And the second component is what we call the acoustic model, and it's actually the likelihood of the source given, the signal given the source, right? So you have these components. And then you have the third term here, which is the decoding step, where you try to find the maximum, you try to find the sequence of words that maximizes this product. Okay, so let's look at each of these components separately. The first is the language model. So why do we need the language model? You could say, let's keep a uniform prior probability over all the sentences in the language. Well, that's not quite right, because sentences are not all equal probable, as you can see here. This makes sense, this doesn't, in most contexts. So the language model is important to actually disambiguate a speech signal that is acoustically confusable, right? And there is an example here of things that, if you just listen to one part, you don't know what it says, but
Right one.
What does it say? What right one? Right or left? Right? You can have many interpretations, right? So you have to know the whole context to know what it said.
Give me the right one.
Right. Now there is no confusion because you have the whole context, like versus this one.
I'd like to write one.
Very simple example, but